courses. And so this is the fourth installment of Sobhan's course. He will continue, he will recall, and I should say, the floor is his.
Thank you. Okay, so today's goal is to try and wrap up the proof of the theorem I stated at the beginning of the first lecture, which was the group of compactly supported area-preserving homomorphisms of the disk is not a simple group. You can talk for them in subgroups. What we recall, this was done in collaboration with Cristofaro-Gardiner and Humiliére, with friends and collaborators. And the proof I'm about to present to you today, in the first lecture, is based on a later proof that we discovered, the three of us jointly with Mak and Smith. And now then, we forgot about everything about area-preserving homomorphisms and spent two lectures talking about Floer homology and spectral invariants, and we got what was called Lagrangian. Today, we're going to use those Lagrangian spectral invariants to finish off with. Now, in the first lecture, I outlined what the proof of this non-simplicity result was. I said there is these magical numbers or magical functions, which we call linked spectral invariants. But the word spectral invariant, you kind of know. We'll see what linked spectral invariants are today. I call them C sub D. So there is a sequence for every natural number. There is one of these. They eat an area preserving the homomorphism and give you back the real number. And they have the following essential two properties. There were a bunch of properties, but I recall these two that were important for our proof. One was the Calabi property that allowed us to connect these things to the Calabi. And it said the following. You take an area preserving the homomorphism of this. You could always write it as the time one map of some Hamiltonian isotopy. So I'm writing it as the time phi h denotes a time one map of a Hamiltonian isotopy generated by some Hamiltonian. Now, if you look at, so phi h is fixed, and you look at CD of phi h, the sequence of real numbers converges in the limit to the average of the Hamiltonian. That's the key property that allowed us to connect these to the Calabi. Right? We don't even need to this is the Calabi, but we don't even need to recall that. And then there was a third property that said these are actually continuous in the C0 topology, and we can actually extend them to the group of homeomorphisms. So this allowed us to extend them to some subgroup of the group of all area preserving homomorphisms. Today we are going to focus on two things. I will define these linked spectral invariants. We'll see they're a form of Lagrangian spectral invariants, and then we will prove this property. So our goal is to prove this. Okay. And this is just, there's not enough time to go. So let's recall what we did in the last two lectures. A recap of where I finished off in the previous lecture. We take a Lagrangian, we fix a symplectic manifold and a Lagrangian inside. So Lagrangian, recall, is just a submanifold. If this is dimension 2n, this is half dimensional, and it's such that omega vanishes on this submanifold. The kernel, the tangent space, declare two vectors from the tangent space, you just get back to it. Get zero symplectic there. Example that's relevant to us, if you take a curve on a surface, it's a Lagrangian, but you could also take product of curves. The gamma 1 times gamma 2 in this picture is a Lagrangian submanifold in the product. This is the sort of example that's going to come up in 5 minutes. Okay. And then we saw if the relative phi2 of the Lagrangian is 0. So this means every disk that has boundary on the Lagrangian can be homotoped into the Lagrangian. Examples of these. Then, for a generic Hamiltonian, and the genericity condition or non-degeneracy is that when you apply it to the Lagrangian, you apply the homomorphism to the Lagrangian, you get something, the image is transversed to the Lagrangian. Then you could define, firstly, these groups called Lagrangian Floer homology groups. There's a theorem that says they just recover the singular homology of the Lagrangian submanifold. And then we saw that we could use this. There's an action filtration, which I won't recall, but I'll just say a few words, that it allows us to define Lagrangian spectral. So you fix a class homology class alpha, and we define L of alpha comma H to be the infimum of values A, such that alpha can be seen action level A. If you recall, this A here stands for, we look at the part of the complex where you think that action level. So just recall, if A is very, very small, this filter, this homology at level A was 0. And if A is very, very large, then the homology is everything. So at some level, you switch from, for small values of A, you're not able to see the homology class alpha, and for large values, you're able to see it. So at some point, the switch happens, and that's what we call the spectral. All we're going to need to know for today's talk is that this number is well defined and has a nice property. A key property that I recall last time, that I stated on the board at the end of the talk, called the Lagrangian control property. And it's stated as follows. So we take two Hamiltonians, H and F. Then we want to compare the spectral invariant for H to the spectral invariant for F. And we get this next part. We look at the difference between H and F at time t. We take the maximum over the Lagrangian and we integrate the spectrum. Then over. That's why it's called Lagrangian control. It really is. It tells you that these values basically there is. If you understand the Hamiltonian and the Lagrangian, you have a good understanding of these spectral. In general, they're extremely hard to compute. And you could see the definition was quite complicated. So it's not easy to actually compute them. What you could do is try to estimate them properly. Now, one thing you might note is that this quantity is actually less than equal to the sup norm of H minus F. And this side is less than equal to the minus. Okay. So as a corollary, you see that this function, a fixed alpha, when I view this as a function on the space of Hamiltonians, it's Lipschitz with respect to the sup norm. Therefore, it extends to the closure, which is all C0 function. Why? Yes, we could. I actually, it is. We could squeeze it in between this minus that. It's the L1 infinity norm. It's called the Hofer norm. But okay, this that's usually actually how the symplectic geometers prefer to talk about it, but I decided not to talk about it. So this is Lipschitz, and therefore it extends to C0. So we have it well defined actually, the continuous function for which the Hamiltonian flow is just not involved. Okay, this is going to be the key property we're going to use. And I'll come back here and I'll tell you what the Floer homology is. So what I'm going to do now is goal for today, for the rest of today's lecture, goal is construct CD as the function on the space of, smooth or C0 functions. We're going to extend the same way to the C0 functions on Hamiltonians on the sphere. So not on the disk. You're going to work on the sphere, right? But the disk sits inside the sphere, so you play something on the disk. But I'll kind of forget about this from now on. We'll construct this as a function, so as something that takes the Hamiltonian on the sphere and gives back a real number, and we'll show that two-hole. We show that CD of any function h as d goes to infinity converges to this form. Quantity given by the below. Okay, so that's what we'll do. Then there's a bit of juggling around to get the rest of it, but for lack of time, I just won't say how to do it. So you just see what the construction of CD is. This tells you immediately how to get it for functions on the disk. Then you have to do some work to show that it just gives you something well-defined for Hamiltonian diffeomorphisms, and then there's zero continuity and so on. So that part is just not enough time. Okay, so that's the goal for today's talk. Any questions? There's quite a bit of stuff to Yes. S2 is the two sphere. Because so the problem is that for the here, yes. So okay, maybe I'll say this. I mean, remember we want actually functions on the disk, and we want these invariants constructed for Hamiltonian diffeomorphisms. The disk sits inside S2, so here's the disk. I take an embedding of the disk into S2. Right? Then if I define this, the problem is that for Floer homology to work out well, I need to be on a closed manifold. It's not easier to be on the closed manifold. So I embed the disk inside the sphere, then I construct it for Hamiltonians on the sphere, and then I just pull back to the disk. Then you have the invariant constructed for Hamiltonians on. Is that okay? Yes. In the previous lectures, it was not, and today we'll start from the surface and then go to a higher dimensional and construction is part of the path to a higher. So we will actually need Lagrangian Floer homology in the projected space of dimension. And you're going to run into a problem, which I mentioned. What happens if actually I2 of ML is 0, is not? Turns out this is what the problem is that this is more complicated to explain, so I didn't want to explain it. Especially the notation is quite a bit more complicated. Things could go wrong. One is that Lagrangian Floer homology could be 0. Could be 0, or sometimes even not even defined. There are obstructions. Could be 0. Okay, but if it's 0, then obviously it can't equal to the homology of the Lagrangian, and I can't get the spectral. But if then the definition of Lagrangian Floer homology, if it is well defined, depends on the Lagrangian. You actually have to calculate it for Lagrangian. And I'll just say if the pair ML is nice, then all of the above works. But this actually means that you take your Lagrangian, you actually need to do some work on it to show that it's nice. You can't just get it. And I can give you an example of a pair that's not nice. So for example, you take this surface of genus, whatever genus, and take the Lagrangian that bounds this. So this Lagrangian, the contractible surface. Lagrangian Floer homology is 0. Yes, yeah. For us, it's going to turn out to be exactly the singular homology of our Lagrangian. You're going to see a Lagrangian in a few weeks. Then there's a whole theory. It's a vast field, and you might have heard of the people who work on Lagrangian Floer homology and Fathi categories. There's a lot of machinery developed for computing Lagrangian Floer homology. So you could take this machinery and apply it to your Lagrangian and see what it says. your favorite Lagrangian. Okay. So I'll tell you now how we're going to get a Lagrangian that actually gives us these numbers C sub B. So now we go to here's the definition. We just chose this definition because something a Lagrangian link is a finite. So now we're back to surfaces, a finite collection of disjoint circles, embedded circles in let's say S2, for the surface of S2. For some examples, you could take, for example, so they have to be disjoint. You could take a bunch of circles that look like this. Is right there. And here's another example, and this is the example that actually really interests us today. The key example for us is this. I take the two sphere, and then I assume the area of S2 is 1, so I put a symplectic form that gives me area 1. And then I take this following link, which in our paper we call equidistributed. So I take, these are small circles. And this link actually I call L sub D, because there's going to be D circles of equal area. L sub D, so it's L1 union LD. So here's L1, L2, L3. And basically, I put as many as I can, so I'll get LD. Area here, area equals 1 over D plus 1. So to be disjoint, I can put only D of them. Total area inside here is capped by all these disks is D over D plus 1. Therefore, the complement also has area 1. Okay. So this, I mean, this is an elementary. I'm not saying anything deep here. I'm just saying consider this Lagrangian given by those circles. So it's a disconnected Lagrangian for which I will try to build a Floer homology that's very well adapted to our. Well, I should say the strategy. I should say the names of people that inspired our strategy. So Lagrangian links higher to our work. We studied this one, but this one was studied in earlier papers of Mak and Smith, the collaborators that joined us. There's something similar to this. And spectral invariants for such things were defined by Cristofaro and Shulupin. This is really greatly inspired us. And actually, the whole thing was really inspired by something that comes from the early 2000s, the works of, I don't know, Orange, Va, and Java on what's called Figar's Floer homology. So it was kind of sitting in a different community, a nearby community, didn't realize until 20 years later that it could be applied to the problem of real interest. Okay. So right now, our goal is to define Lagrangian Floer homology or Lagrangian Floer spectral invariance for this object, which I call L sub D. So this union of circles on the screen. I should say the disks, I want them to be kind of round and small disks. I don't want them to be spread around. So these are really the choice. The way I drew the picture is the way you should think of it. If you apply symplectomorphism to this thing, somehow it won't be good enough for covering the top part. So somehow the geometry of the picture is actually quite important. Yes? Yes, you should think of the sphere sitting inside R3. take a round circle around the North Pole, and then you move it around with rotations around the sphere as much as you can. So they're all very, yeah. You could just, yes, I mean, this is around maybe with, I think you could do it even with rotations, but even if you can't do it, you could just plot. The point is that what's important is, we'll get to this, so maybe I'm jumping ahead, I should have mentioned. What's important is this diameter is small diameter. So you don't want the disk to be something of area 1/d that goes d+1, that goes all over the sphere. Yeah, they could be a little bit. Yes, that would be okay. That would be. But I'm jumping ahead, so we will see why that's needed in a bit. So we want to define Lagrangian Floer homology for LD. We will do this. Then we'll obtain a spectral invariant, a Lagrangian spectral invariant. Which I'll call L sub D. And L sub D will be, so a mapping from the infinity of S1 times S2 to the real line. And then we'll show, so somehow, then we'll see that this L sub D, so CD is actually defined to be a normalization of LD. CD will be 1/dLD. So we'll get to this, and then we'll see that this has the right property. Okay. So for the moment, we'll just focus on this part where I define the Lagrangian Floer homology for LD. This it's not at all clear how it should be done. And then once you have that Lagrangian Floer homology well defined, and compute it and show that it's got the right homology, then you get this spectral invariant LD as before. Then you normalize, and once you normalize, you realize in the limit you have the right property. So we'll do that. Are there any questions? So now there's going to be a bit of a geometric construction. So there, I'll say what the alpha is. There's going to be a fixed canonical choice of alpha. So now there's going to be a geometric construction. Yes.
Is it possible to do all this machinery on higher genus surfaces?
Yes. Yeah. It works on all surfaces.
Thank you.
Yeah. Yes, so there were some results that I stated at some point during my first talk. Is like the so the result we produced was that the group of area preserving homeomorphisms of the disk is not simple. For all other surfaces, the group of Hamiltonian homeomorphisms of the surface is not simple. And then there was an extension of Calabi to this subgroup, which was called homeomorphisms of O and Muller. That goes through as well. So the results I produce, I show you on the disk, they kind of generalize to in all ways that are not obstructed in obvious ways to other surfaces. So now we need to talk about symmetric products. So for a while there's going to be geometric construction that I have to explain. You have to find. Okay. So we're going to start with that picture, and then we're going to produce a nice Lagrangian in a higher dimensional symplectic map. So the first thing I want you to do is consider S2 to the sphere, default product of the sphere. So S2 times S2 times S2, so D times. Now, this is a symplectic manifold. You could just take the standard symplectic form on S2 and take the product to write something. Now, what I want you to notice is that there is an action of SD on it. You could permute the coordinate. You could take this coordinate and switch it to the other coordinate. That's a symplectic morphism. So there is an action of SD. Therefore, you could quotient out by this action. It's a symplectic action. So we quotient out by SD. So SD is the permutation group. This is the permutation. And the resulting object, and let's take a close look at it, it's called a symmetric product. So it's the default symmetric product of S2. I'll denote it by X for the rest of the talk, by big X. And you'll see in a second we have a symplectic form of it, which is not a very nice symplectic. But before I talk about the symplectic form here, let's examine this object more closely. So as you can see, the action by switching coordinates is free outside of what's called the big diagonal. So it's so there is this object which we call the big diagonal, which is when exactly the points where the action has fixed points. Instead of all points in the product, where two of the coordinates coincide. There exists I and j different such that xi equals this. Right, so it should be clear that the action is free outside of this set. There's no fixed one. Okay. Therefore, this X is a priori a smooth manifold outside of the diagonal, outside of the image of the diagonal. So what you obtain is something that's a smooth manifold, but it's smooth away from diagonal, and on the diagonal a priori it's singular on the diagonal. Or people like to call that big one. It's a symplectic action, so I mean, once you have a free action, symplectic form descends as well. You get a symplectic form also in the complement. But along the diagonal, the symplectic form degenerates and it's no longer something singular. So you get omega singular. Okay, so this is also singular along the diagonal. I use the same notation in the product and in the quotient. So when I say it's singular, I mean it's singular in the quotient. You project the diagonal to the quotient. Okay. Any questions about the construction so far? Now you see why I wanted the circles to be disjoint. So now let's take LD, this our length. So remember, it's the disjoint union of these circles, and therefore I could take the product. So L1 times L. Now this is the product of Lagrangian, so it sits as a Lagrangian submanifold inside the default product of it. Is that okay? So far, this should be clear. But the Lagrangians have no intersection. Therefore, this does not intersect the diagonal. And this is kind of important for us too. So it sits in the complement of it. Oh, you could take the small neighborhood of the diagonal and it sits outside. Therefore, when you pass to the quotient, you get a Lagrangian, which I'll call T because it's a torus. And this torus, so it's a smooth Lagrangian inside this smooth symplectic. Like this, so it sits in the smooth locus of this quotient. There it's an honest Lagrangian submanifold. It's a Lagrangian torus. We want to do Floer homology for this object. But of course, there's a problem. This is not a priori smooth manifold. Let's see, it is actually. This is not a symplectic form. It's only a symplectic form away from this. Now, a bunch of nice facts from basic math come to rescue. Well, you'll see, I mean, at this point, it might look like we're in a lot of trouble. I mean, defining Floer homology on even on for a curve on a torus was quite complicated. Now it might look like we're in hot water, but we'll see that the situation is actually quite nuts. So let me draw a picture first. So here is X, the symmetric product of the sphere. Here is our T, the Lagrangian want to study, and here's delta, this place where everything is bound. Okay. A bunch of nice facts here, kind of like an end, a bit like an angel, is coming for a rescue here. Nice fact one. X is actually can be identified with one of the nicest, one of the favorite manifolds for symplectic geometry. It's the default, it's the projective space of dimension. Okay. Why? It's because to see this is actually Gauss. Gauss is the fundamental theorem about it. So why is X equal to CPD? Well, I'll explain why the default symmetric product of the complex plane can be identified with C to the D itself. And then hopefully why that can be done for CPD. Actually, for any surface, the default symmetric product of a Riemann surface gives you back a complex manifold of dimension. Now, to see this, the easiest place to see this is the default symmetric product of the complex plane. This complex plane away from totality. How do we see this? Let me take a point here. So I'll write it this way. So it's a bunch of points, lambda 1 to lambda b. When I write it in square brackets, it means that you're allowed to permute. Anybody have a guess what the identification is? I don't know. Yeah. Exactly. You send it to the polynomial, which has these roots. So it's d minus lambda 1 times d minus lambda. Okay. And then here, so you see that this doesn't depend on the choice of the polynomial, doesn't depend on the choice of the permutation. I mean, on the order of the roots. And then how do you identify this with C to the D? Well, it's easy because you take the coefficients of the polynomial. So you view C to the D as polynomials of this form. D to the D plus A 1, D to the D minus 1 plus A. You take the coefficient. So it's the correspondence between roots and coefficients of polynomials that's responsible for it. This only works for surfaces. That's why this theory does not, part of the problem why this theory does not generalize to higher dimensions. Okay, so now we have this manifold, which is CPD. That's fantastic. And now here's nice fact 2. So the roots show that the following is true. So you have a nice symplectic manifold. Inside it, they have a Lagrangian torus, but there's still the problem with the symplectic form. However, there is a construction that's not so bad. Don't remember off the top of my head. It says you could actually modify the symplectic form just in an arbitrarily small neighborhood here. So you could, so here we have omega singular. Of course, the singularities are all along this codimension 2 subvariety, and you could modify and replace with another symplectic form, which is now smooth, and I call it omega p equal to root. So you could kind of modify the symplectic form, leaving everything where the Lagrangian lives kind of very close to the diagonal, and change this to a smooth symplectic map. So the summary is this. 1, and modify omega sing to near delta to get the smooth symplectic form, which I call omega. Okay, so now you have a Lagrangian on a smooth symplectic map. Things are starting to look better. But it gets even better. CPD has a canonical symplectic structure called the Fubini-Studi structure. So CPD is a quotient of C to the D plus 1. C to the D plus 1 is R2D plus 2. There is the canonical symplectic structure on C to the D plus 1. this canonical symplectic structure descends to the quotient and gives you what's called the Frobenius study. So it turns out that this is actually the Frobenius study form of the symplectic model. So omega p can be identified with the Frobenius study. You should just think of it as this. Those of you who've not seen it, just think of it. You should know that there is a symplectic form on CPD, which is very well understood, and people have been studying it for a long time. And this is actually equivalent. If I can find a diffeomorphism of CPD that pulls back this form to the standard. Okay, so in reality, we are now on CPD with its standard symplectic structure. This is an object that symplectic geometers have studied quite a lot. Now, we want to do homology in a setting that people are comfortable with. And what we have to do is study the homology of this Lagrangian. And what we prove in our paper, we prove that, so as I said, but now the problem is that pi2 of ML is not zero. And you could see this even on the sphere, because each one of these disks that bound the circle, they lead to a disk with boundary on this torus. So there's plenty of this. But there is a way to compute Floer homology, and we computed it, and we showed the Floer homology of this Lagrangian T. So if I pick a Hamiltonian H and study the Floer homology, and this is actually non-zero. Not only is it non-zero, it's actually just equal to the standard singular homology. Yes. Or any choice of it, yeah. So actually, there is a theorem. There are general theorems that say Floer homology never depends on the choice of it. So just you compute it for one H and you're done. There is a whole theory of how you're supposed to do it. So as you saw, the obstruction of defining Floer homology were disks with boundary in the Lagrange. Now there is something called like the pseudo potential. People in mirror symmetry talk about a lot. A function that basically keeps track of all the disks. What you have to do is you have to understand all the disks with boundary in the Lagrange. Once you understand that, then you are able to say things about homology, whether it's zero or not. And in this setting, it's actually because you could associate there's a correspondence between this with boundary and Lagrangian T and stuff that you see on the surface, you're able to. This is in different forms. This was already kind of when we did the paper initially, we didn't realize this, but this was already present in the works of in somehow a different language, a somewhat different setting. It was present. Something similar to this is present in the works of Sobhan and Jabo from 20 years. The non-zeroness of this Lagrangian Floer. Okay, so we have our Lagrangian Floer homology, and therefore we can define Lagrangian Floer homology is non-zero. So maybe I'll put a D here because the dimension, let's keep track of the dimension D here. And therefore I can define my spectral invariant just as before. Okay, so we'll come back to this picture. Okay, so now I can define, as before, you can define the Lagrangian spectral invariant. You take H, a time-dependent function on S1 times. Now you have to work on X, which is CPD, and you have to take a non-zero homology class, which was alpha before. But now I'll just take the fundamental class of the torus. I can just take alpha. So I'm taking this to be alpha. Okay. So then I define. Any questions? The fundamental class is always there, right? Torus of dimension D. I take the fundamental class. I think actually it doesn't make, as long as I take any, we'd also take the point class. But I'll take the fundamental class because that's everybody's favorite homology class. And so I define LV of H to be L, the Lagrangian spectral invariant associated with the fundamental class. And so now we have a Lagrangian spectral invariant that's defined for functions on default symmetric product. But what we want is functions on the sphere. But we want spectral invariants for a function called this H, maybe I'll call it for F, a function on the sphere, a Hamiltonian on the sphere. So how does this work? It is rather easy. You could lift a function on the sphere to a function on the default symmetric product. You take this F and consider its, so it's F, correct some, this is the notation F. So that means, what does this do? I give it a collection of points x1 to xt, and this just associates to this the sum. Yeah, I mean, each one of these depends on time, so it's actually time dependent. Now note this, so a priori this lives on the default product, but it's invariant under this, the action of the symmetric group. So I could switch and nothing happens. Therefore, it descends to a function on the default, on the symmetric product. So this is SD invariant. So then descends to the quotient and it defines a function which we call SIMD. Okay, so just spell it out again. We take a point in the default symmetric product, and SIMD of F is just the sum. Okay, so I have a function on the default symmetric product. It's actually not a smooth function. It's smooth away from the diagonal, but the long diagonal is only bullet. But it doesn't matter because spectral invariant, like I said, can be defined for C0 functions. So then I can define spectral invariant. So the general theory gives me a spectral invariant. So LD, of this function makes sense. Okay, and this is what I call, basically, this is what I call, so I wanted something that's defined on the sphere, right? This is what I call C sub D of that. Except that it's just more convenient to multiply by one of these. Okay. So now this construction gives me, so I have this mapping CD that takes a function, actually a continuous function, but anyway, takes a function, a continuous or smooth function, it doesn't, smooth Hamiltonian matter on this and gives me back really. And that's the C. Okay. Any question? I'll tell you what the C is. I'm not actually quite a time for proving that it recovers, which allows. Yes. Yeah, that's okay. Up to here, we've not used that properly. We're going to use it for proving that the next part, okay, the limit to recover the average of it. Yes, 1 over D. Is 1 over D is just no, because then it was easier when writing the paper to write CD of H converted to the average of H than writing 1 over D CD of H. So, we had this debate 50 times, which one on. Again, we went with this. But the 1 over D is not too important. Any questions?
Excuse me.
Yes.
What does this has to do with the periodic points of the initial flow on the sphere?
Oh, that's a great question. So remember that's a great question. So you're asking, what does this have to do with the dynamics on the surface? So what does Lagrangian Floer homology detect? It detects, remember, it's not periodic points, but it detects chords, Hamiltonian trajectories that start and end on the Lagrangian, right? And our Lagrangian now is this torus on the default symmetric path. Okay? Now, this sim D of F, although it's not smooth, it's smoothed away from the diagonal. And if you look at its flow, so the flow away from this region, the flow of sim D of F makes sense, and it looks like this. So sim D of F, the flow, you can look at its Hamiltonian flow, and it looks like this. It takes a bunch of points x1. Well, so phi t of sim df applied to x1. xd is equal to this, phi tf of x1, phi tf of x. It's actually just, so you just apply the flow coordinate one. Okay? And this defines some smooth Hamiltonian flow away from the diagonal. Along the diagonal, it does something that I don't understand. The reason the flow is that way is because basically this is like the product of vector. Near the diagonal, it does stuff that I don't understand. It depends on how you do the smoothing. I have no idea what it is, but that doesn't, because the diagonal will never come. You pick this neighborhood such that the image of diagonal under the isotope, you never actually. So this allows you to try to relate a Hamiltonian chord, so a Hamiltonian path that starts here and ends on the Lagrangian to something on the surface. And it looks like this. So this is now S2. And I have my my Lagrangian link. So let's stop there. So a point on that torus is a collection of 4 points here. I have to pick 4 points, one on each one. And then you flow these points. So what you get is you start flowing and you apply, this tells you apply the Hamiltonian flow to each one of the points. So you get, so let's call this x1, x2, x3, x4, xd. And when you flow this, you have to end up back on the torus. So that means this, for example, x2 is the trajectory of the Hamiltonian that starts on this circle and it has to end on another one of them. Now, x1 has to do the same thing. So it could start here and end, for example, on the same circle. And x3, well, it has to start here. Now it has to end up on the torus, so it can't be back on the same component. It has to be on a different component. So it has to go here, let's say. And then this one has no choice but to go here. So it's basically a collection of paths that go between the circles. So maybe the only subtlety is that why x3 cannot. Remember, the initial point had to be 1 point on each of the components. The final point has to be, so it's d different points, one in each component. The final end of the trajectory has to be d different points. So that's why x3 can no longer come back to x3 because this one comes back. So it looks like paths like that. And then actually you could read in some way that it's more complicated because you could even read the action somehow on the surface. Although that it should be possible. I haven't tried to. Okay, so we're really counting objects that the Floer homology can be described in some ways directly on the surface. So the generators of the complex are chords that look like. Okay, does that answer your question?
Yes, thank you.
It's a great question. Okay, so now what do? I try to prove the Calabi property. remember what this says. I'll write it here. So start working towards it on the other board. So Calabi property of these invariants is that CD of H as D goes to infinity, it covers just the average of it over time and so on. Okay, that's what we want. Now we're going to use this Lagrangian control problem. So we call what we call Lagrangian control. And now you're going to see why I want this to be control. It said, so I'll just state it in the form we use. If I take a function, for now take just G a function on with any symplectic manifold, if you do S1 times n, and then Lagrangian L. Just a general setting, as soon as Lagrangian form homology is defined, then L of G, or any actually alpha, L of alpha G, he said was less than equal to maximum of G over L for each time, and then you integrate with respect to time. And here, minimum of G over L is integrated. You're going to take this and try to R set. So apply this to our setting. So instead of G, I'll take a function with F or G. We'll go we took F, a function on the circle. So let G be in D of F. Just to make notation, simplifying assumption, it just makes notation easier. So assume if T equals F0. So it doesn't depend on time. It just makes the notation simpler, so I'll just go with that. Now read this properly. You just go and sit down for like 5 minutes and think about what it says in R setting. Try to interpret it in terms of, it says that the Lagrangian spectral invariant is between the maximum of a sim D of F over the torus and the minimum of sim D of F. If you try to come and read this on the surface, it says the following. It says CD of F. Well, I used H here and F here, so I hope that doesn't cause confusion. So it says CD of F is less than equal to 1 over D. I could even write it out. So it says CD of F is less than equal to 1 over D maximum over T in D of F. So that's just I'm just spelling it out. And then this implies, you just read what the definition of CD of F is. It says CD of F is less than equal to 1 over D sum. Actually, I'll write it on the bottom board to 1 over D sum maximum of F over Li. And then on this side, you have 1 over D maximum of F, minimum of F, minimum of F over. This first line is just a directed application of the top line, and then going from here to here, it's just remembering that CD of F is defined here. No, this is the Riemann sum for the interval. Upper Riemann sum, the lower Riemann. And we'll see, this is very useful factor in so forth. You now see it on the picture. So, what we're doing is going through here. On each circle, let me erase this. So on each circle, I pick a point where this is maximum of f over that circle, like over L1 on the right-hand side, and I'm multiplying it by 1 over d. That's almost this area. This area is 1 over d plus 1, but that doesn't have any effect. So you see that this is actually the Riemann function for the integral. So as d goes to infinity, you get the d of f less than or equal to. So this is upper Riemann sum. This is a lower Riemann sum. Now we're done. This is the other, this is the integral of that over the surface. And now it's the same thing on the left. Limit. And that's it. That's the proof of the Kalam. There's still some more work, of course, to do. I mean, I worked on the sphere. You still have to do a little bit of work to show things work out like this, but it's not that. Okay, I'm done.
Thank you very much. There's just a few more moments for questions, additional questions. If questions occur to you later, you might buy him lunch and talk over lunch.
Thank you.
All right, so many thanks for this mini course. Thank you for making the homeomorphism group sound simple, although it's not. This is great. I'm very grateful for what you made happen. Quite a miracle. So then, this is the short break. If you're not quite sure whether you're going to make the next talk, do keep in mind that the next speaker can cancel your taxi, your room reservation, maybe even reimbursements. So we will meet here again at 11:30 sharp. Thanks again.